Hi, my name is Gabriel. Welcome to this exam revision session on the five-step method in the continuous case. So, please pause your recording, read these instructions very carefully, then when you're done, you can start off your revision. Now, under this revision session, I've got 3 questions. One taken from the September 2013 and the other one taken from the September 2014 and the last one taken from the September 2016. Now, I selected these questions on purpose. That's because they teach you certain things and all of them are extremely demanding. So let's see our first question. So, in fact, before I do this question here, which is extremely demanding, can you please allow me to derive the price of the European coal option using the 5-step method in continuous case? Okay, so what I want you to do right now, what I want you to allow me to do is to derive the formula which says CT is equal to ST phi of D1 minus K R into T minus equal T phi of D2. Okay, now obviously this will teach you a lot of things and you're going to apply what I'm going to do here in other problems. Now, in order to derive this, we start off with the formula we derived in our 5-step method, which says the price of the derivative at time little t is equal to e to the power minus r into t minus little t times the expected value under the risk neutral measure of your payoff at maturity given the past history. This formula is extremely important. You need to know it going into the exam. Now, I'm going to use this in order to derive the price of my call option. Now, if you remember, the payoff for the price of the call option is the maximum of ST, your share price at maturity, minus K or 0. So what am I going to do here? Now, I want the price. I'm going to use this formula. This is the payoff. Okay, let me substitute to my 5-step method formula. So what am I going to have then? I'm going to have VT is equal to E to the power minus R into T minus little t times the expected value of the maximum of ST minus K with 0 or 0 given the past history. Okay, now in order to avoid a complicated algebra, I'm going to leave out this here and I'm going to deal with this part of the expression, okay, which is the expected value of the maximum of ST minus K and 0. Okay, now if you remember from your basic statistics, you know that if I have the random variable x and I ask you to calculate the expected value of x, now if this here is a continuous random variable and I'm asking you to calculate the expected value of x, you're going to say, well, Gabriel, that is no problem because this is just the integral from minus infinity to infinity of x times f of x dx. Okay, so it's just the integral from minus infinity to x. So the values of x this distribution will take, right, times x, which is here, right, times f of x, which is the distribution of x, times dx. Okay, so I'm going to apply the same thing here. So when the maximum is equal to st minus k, what am I going to have? So I'm dealing with this part here for now. I'm going to have the integral from minus infinity to infinity of st minus k, right? Now you can see here k is a constant. Okay, k is your constant, it is your strike price, but your st is the share price at time t, and the share price are changing in the market. So we have a distribution for a share price. So I'm going to multiply this whole thing by f of st dst. Now, do you agree with me then that when the maximum is 0, I'm just going to have this when the maximum is now 0, which is just 0, so it won't make a difference. So I won't even bother writing this expression here. So now I have this. But now you've got to be a little bit careful, because do you agree with me that the maximum here will only be st minus k if st is greater than k. So if the share price at maturity is greater than k. So now I have a condition on st. I know that my st must be greater than k, which means the values that st can take, it needs to take values greater than k. So my limit of integration now will change. It will be no longer from minus infinity, but it will be from k. Okay, so I'm going to have k there. Okay, let me simplify my expression there and see what we're going to have. So I'm going to have the integral from k to infinity of st times the distribution function of the share prices minus the integral from k to infinity of k times the distribution function of the share prices dst. Okay, now you're asking me, Gabriel, what is the, now just a little warning here, this expected value is under the risk neutral world measure Q. Okay, now you're asking yourself, what is the distribution of the share prices? Well, you'll remember that the share prices follows a geometric Brownian motion, and we have the stochastic differential equation of the geometric Brownian motion given in your tables. Now, this here is under the real world, okay, but we are in Q. We are in the risk neutral world measure, which means my stochastic differential equation will be like this here, okay. So under the risk neutral world measure, this will be my stochastic differential equation for the share prices. And if you remember correctly, we derived the distribution of the natural log of st. I did derive this distribution when I was doing revision on stochastic differential equation, and I said the natural log of st is a normal distribution with mean natural log of s little t plus r minus a half sigma squared into t minus little t and variance sigma squared into t minus little t. So what does that mean? This means that my st will actually be equal to what? Now I'm going to exponentiate on both sides, and remember the exponential of the normal distribution is a log normal distribution. So I'm going to have a log normal with mean natural log of st plus r minus a half sigma squared into t minus little t and variance sigma squared into t minus little t. Okay, Now I've got the distribution of the share prices at maturity. Now, how is that going to help me? How will that find me? How will that help me find me? How will that help me find these expressions here? Well, now you're going to go to your tables, to your orange book. Okay. Now let me get my tables here so that I can explain this to you in a nice way that you will never forget. Now, if you look at your tables, we are given on page 18 the truncated moment of your normal and your log normal distribution, because if you look in your tables, you will see that if I have that X is a log normal distribution with mean mu and variance sigma squared, then my tables tell me that the integral from L to U of x to the power k f of x dx is equal to e to the power k nu plus a half k squared sigma squared, all that multiplied by the cumulative distribution function of the standard normal evaluated at u sub k minus the cumulative distribution function of the standard normal evaluated at L sub k. Now you are given that L sub k is equal to the natural log of L minus mu over sigma minus k, right? And we are given that u sub k is the natural log of u minus mu over sigma minus k sigma. Okay, how will that help me? Well, if you look very carefully here, I've got s to the power 1. Okay, I've got s to the power 1, which will correspond to x to the power 1 here. Okay, and if I look again in the expression, I've got f of st, okay, which is the distribution function of the log normal. So this here is actually matched with this here, okay, and you're going to apply this formula here to these two integrals. So my first integral, let me do my first integral. I can see that in my first integral, it is this thing here, but with k equal to 1. So what am I going to have? I'm going to have e to the power, my k is equal to 1 because I've got st to the power 1. E to the power mu. Now mu is your mean of your log normal distribution. But in the situation of share prices, the mean of your log normal distribution is this thing here. Let me highlight it. It is this thing here. Okay, that is your mean. So that you're going to substitute for your mu. So what am I going to have there? Now let me get my paper because I can't keep on going up and down. Now, what am I going to have there? I'm going to have the natural log of st plus your r. Oh gosh, let me quickly check something. I think I made a mistake here. Okay, yes, I've got r, it's fine. R minus a half sigma squared into t minus little t. Then my formula says plus half, here, look here, half k, which is 1 sigma squared. So I'm going to have half k squared, my k is 1, but my sigma squared under the share prices is this here. Okay, so I'm going to have half sigma squared into t minus little t. Now, and then I'm going to have phi of u of k. Okay. Now u of k, u sub k is equal to the natural log of your upper limit. Now, if I look at my upper limit here, it is infinity. Okay. So I'm going to have the natural log of infinity, which is infinity. Okay. And I'm going to subtract mu, which will just be a number. So I'm still going to have infinity. Then I'm going to divide by sigma, which will still be infinity. I'm going to subtract k sigma, which will still be infinity. So I'm going to have the cumulative distribution of the standard normal evaluated at infinity. Okay. Now there, I need to subtract the cumulative distribution evaluated at L sub k. Now L sub k is this expression given here. Okay, so I'm going to have the natural log of L, which is my lower limit. So I'm going to have the natural log. Now if you look here, the lower limit is k. Okay, so I'm going to have the natural log of k minus my mu. Now my mu under the share prices is the natural log of ST, all that I've been showing you. So I'm going to have the natural log of ST minus R, okay, minus a half sigma squared, right, into T minus little t, so that minus my mean, right? All of that divide by my standard deviation. Now my standard deviation under the share prices is the square root of this. So what am I going to have? Taking the square root of that, I'm going to have sigma times the square root of t minus little t. But I need to subtract k sigma. Okay, I need to subtract k sigma. But my k is 1, so I need to subtract sigma, which is my standard deviation. So I need to subtract there my sigma square root of t minus little t. I see I don't have space there. I'm going to close that bracket. I'm going to close that big bracket. Okay, now that is my first integral. Now my second integral, now I'm going to say minus my second integral. Now you can see in my second integral, I actually don't have an ST. You see here, let me show you using a different pen. You see here, I don't have an ST. So in actual fact, my K is equal to 0. Okay, now I'm going to apply my formula again on page 18 with K equal to 0. Okay, let's do that and see what we're going to get. So I'm going to have minus k, all that multiplied by phi of u sub k, which will be infinity because my upper limit is infinity, minus the number divided by a number minus something will result in it will result in infinity. So I'm going to have minus infinity there. So then I'm going to have minus. Now remember, you're going to say minus k sigma there, which remember your k is 0, which will just be 0. So now I'm going to have phi of L sub k. Okay, so what am I going to have there? I'm going to have the natural log of my lower limit L, which is k in this case, minus my mu, which is the mean, but under the share prices, the mean is the natural log of ST minus R minus half sigma squared into T minus little t, divide by your sigma. Now under your share prices, your sigma is sigma square root of t minus little t. Now I need to say minus k I need to say minus k sigma here, but my k is equal to 0. So I won't have that term. Everything will just be 0. So I won't have this here. Okay. So let me nicely write my expression, because I see here I've got a little bit of a problem. Most of you can't see, I guess. So let me rewrite it again in a neat way. Now, if you look here, you will see that my e to the power of the natural log of st, that will cancel, and I'm just going to have st, okay, times e to the power of this whole thing here. Now I've got minus half sigma squared into t minus little t, which will cancel with this positive half sigma squared t minus little t. So what am I going to have then? I'm going to have st e to the power r, okay, into phi, the cumulative distribution evaluated at infinity, minus the cumulative distribution of the standard normal. Now let me write this nicely, because I guess you can't see it. So I have the natural log of k minus the natural log of st minus r minus half sigma squared into t minus little t divided by sigma square root of t minus little t minus sigma square root of t minus little t. So that is what you have then. So minus, so nothing major I'm doing here. I'm just rewriting my expression. So what am I going to have there? I'm going to have minus k into the cumulative distribution of the standard normal evaluated at infinity minus this thing here. I won't do a thing here. I'm just simplifying so that you can see the whole expression. So I'm going to have the cumulative distribution of the standard normal times the natural log of k, natural log of st, minus r, minus half sigma squared into t minus little t, divided by sigma square root of t minus little t. Okay, now here comes the interesting part of this derivation. Now, I want you to think about this. Let's go down with our steps. So what am I going to have here? I'm going to have st e to the power r. Now, here, I want you to be careful here, because the cumulative distribution function of the standard normal evaluated at infinity is actually equal to 1. Okay, if you look at your tables, you will see that as the x value is growing, as the x value, which is this infinity here, is growing larger and larger, your cumulative distribution will approach 1. So what am I going to have then? I'm going to have 1, right, minus phi of, now this is the tricky part of this proof here. Now look this here. Now I'm telling you now, believe it or not, I'm telling you now that this expression here is equal to minus phi of d1. Okay, that is true. Now you're saying, Gabriel, I am not happy because number one, d1 in the tables is something else. If I take the negative of it, I also won't get this. Now, believe it or not, this expression here in blue is negative d1. Now, in order to convince yourself, because the algebra is a little bit complicated, in order to convince yourself, I would advise you to take values for k, st, r, and sigma. So just choose random values for k, st, t minus little t, sigma. Substitute them here, right? And substitute them again in your in your expression in your tables and take the negative and see if you won't get this value here. So convince yourself numerically. You will see it is true. Okay, let me continue. Now, I'm going to, now just something here, just a little warning here. Here, just look here, don't make a mistake. You see this t minus little t is multiplied into half sigma squared and into r. So please don't leave it going down. So I've got r into t minus little t. Okay? And what have I got? I've got r into t minus little t. Now let me continue. Now I've got minus k. Now do you agree with me? This will be equal to 1. Now again, believe it or not, but this is the cumulative distribution of the standard normal evaluated at minus d2. Pick numerical values in order to convince yourself. Okay, now I'm going to simplify this and say, okay, what have I got here? I've got st e to the power r into t minus little t into 1 minus, now do you agree with me that this is just 1 minus phi of d1? We have been doing this when we were calculating the cumulative distribution of the standard normal probabilities, so I'm sure you are familiar. Minus k into 1 minus, and this here is just 1 minus phi of d2. Okay, so what am I going to have? I'm going to have st e to the power r into t minus little t into, now do you agree with me that these will cancel and you're going to multiply the negative and you're going to have phi of d1. Okay, now there is no need to put the bracket because I've just got 1 term. So I'm going to have phi of d1 minus k into, these will cancel and I'm going to distribute the negative inside the bracket and I'm going to have phi of d2. Well, this is not exactly the price, but it looks familiar. Okay, let's go back to what we want to prove. We want to prove this here. Now be careful, the expression I've just derived, it is this part here, if you remember very well. It is this part here. So in order to get my price, I still need to multiply the part I've got by e to the power minus r into t minus little t. So that is exactly what I'm going to do. So I'm going to say now the price of the call option is equal to, now I'm going to multiply this whole thing by e to the power minus r into t minus little t. Do you agree that these here will cancel and I'm going to have st phi of d1 minus k e to the power minus r into t minus little t, the cumulative distribution of the standard normal evaluated at d2. And oh my gosh, isn't this lovely? Isn't this wonderful? Because now you have got the price of your call option. Okay, I always love it when you get what you are required to prove. And you can always do the same thing for the put option, which has the payoff of the maximum of k minus st0. So I'm going to leave it to you to derive the price of the put option. Okay, now you're saying, Gabriel, why are you doing this? Well, what I'm trying to show you is that always, if you have got the payoff, okay, and you have got the distribution associated with the payoff. Now your payoff can be anything now. It can be st squared, it can be s1 minus 200, it can be anything. If you have got the payoff and you have got the distribution associated with the payoff, this is a procedure you're going to follow when the examiner is asking you to derive the price at time little t. Okay, so this is the procedure you will always follow. Okay, so I'm showing you this because this is what you will always do. And you will always come to your truncated moment of your log normal distribution. Okay, now that is not part of our question, but I did this to show you the importance of the distribution of the share prices and how to price a derivative when you are given the payoff using the formula we derived in our 5-step method. Okay, let's look at the actual question here that we have. It is a very demanding question. So the question that we're going to be looking at is taken from the September 2013 CT8 examination. And it goes like this.